So now that we have a good idea about what a multivariable function is and what it represents, say graphically in 3 dimensions, or even if we can go up to 4 dimensions, the next thing we need to start talking about is limits, which will eventually lead us into derivatives, which will then lead us into integration. But we really need to start with limits to get into that. And so we're not going to spend a ton of time here with limits. Really, this is just a mechanism to get us into derivatives for these multivariable functions. But we do need to talk about it. So a couple of terms we need to get into. One, it's the concept of what we call a delta neighborhood. Okay? So we can look at the definition. In this case, a delta neighborhood about some point, say x sub 0, y sub 0, is any point in the disk centered at x sub 0, y sub 0, where the radius of the disk is delta, which is greater than 0. And delta, essentially, neighborhood could be defined using this definition. In this case, here's your circle formula, and that would be represent the radius that is somehow in this delta. So what is this delta neighborhood? Well, essentially what it is if you look at a particular point, we call, say, like, look at this point right here. We'll call this point x sub 0, y sub 0. And we look at a little ring around that point and all the points contained inside that ring. So all these points in here, this would be considered our delta neighborhood around this point x sub 0, y sub 0. And so you see this in this picture here. Here's your delta neighborhood around that particular point. Any point that's inside the disk is basically what we call inside the delta neighborhood of the center point. All right, so then we have a region. And what we want to talk about is the difference between an interior point and a boundary point. So an interior point for some region R is any point x sub 0, y sub 0, such that there exists a delta neighborhood with its center such that the entire delta neighborhood is inside the region. So I look at a point, I look at its delta neighborhood. Again, and something I should say is that this delta neighborhood around this point is an infinitely small radius around this point. But nonetheless, it's a collection of points that sit around a given point. So if that delta neighborhood is completely inside the region, and what you see here for this point right here is that this delta neighborhood is completely inside the region, then we consider that to be an interior point to the region, as opposed to a boundary point where the delta neighborhood that's centered at x, y is not completely inside the region. That some of the points are inside the region and some of the points are outside, and you kind of see that right here with this point. So if you sit right on the edge of the region, and I'll blow that up here, if you have your region that looks like this, and here this would be the inside of the region here, this infinitely small delta neighborhood is completely inside, where this point that sits here, part of my delta neighborhood would be outside and parts of my delta neighborhood would be inside the region if this was my region R here. And no matter how small I make this delta neighborhood, infinitely small, if I zoomed in 1,000 times, still part of the delta neighborhood would be outside and part would be inside, just making that a boundary point. And then we would consider the region to be open if it does not contain the boundary point. So all these points here that make up the boundary, if these are not contained in the region, then we consider the region open, and oftentimes what we would do is we represent that by, say, like a dotted outline of the region. Okay? If the region is closed, then it would contain those boundary points. Okay, so then we would make the solid line across. So that's just a couple of things there as far as what a delta neighborhood is. Concept of interior point, boundary point, open versus closed region. What we really want to talk about, though, is the concept of a limit. So here is our formal definition of a limit, similar to the formal definition of a limit you saw back in Calc 1, which was your delta epsilon definition. For a limit, this is very similar. So let f be a function, okay, of 2 variables. So we're only going to do this for 2 variables so that we can make sense of it graphically as well in 3 dimensions. That's defined, except at every point, except possibly at this point, x sub 0, y sub 0. So it's defined around x sub 0, y sub 0, but not necessarily at this particular point on an open disk centered at x sub 0, y sub 0. Okay. Let L be a real number. Then the limit as xy approaches x sub 0, y sub 0. Now remember, with these two variable functions, our domain is a series of points. So in Calc 1, x would be approaching some value c because your domain was just a set of x values. Now your domain is a set of x's and y's. So xy will be approaching this particular point, x sub 0, y sub 0, for f of x, y. That would equal some limit L if for each epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of f of x minus L is less than epsilon whenever the delta neighborhood around x sub 0 is less than delta. What is this saying? Well, it's basically saying the same thing that you were saying back in Calc 1. So what you were saying in Calc 1 was this. If I had this particular value here that I was trying to approach on the x-axis, so x was approaching a, I would have to approach a from the left and I have to approach a from the right. And the idea here is that as x got close to a, the corresponding y values would have to get closer and closer to a particular y value, say L. So this would be L minus epsilon, this would be L plus epsilon. Epsilon is the distance that I got close to my limiting value. Delta was always the distance here, so this was delta, this was your delta. This distance here was your epsilon, and the idea is when delta gets small, epsilon has to also get small, thus approaching this particular point. So the y value gets closer this way, the y value gets closer this way, and you approach this single y value here. And we basically said that, for a limit to exist, it would exist such that when f of x minus L is less than epsilon, okay, that'll happen when, x minus c is less than delta. So what you said here is that the distance between x and c, or in this case x and a, when this distance gets small, this distance had to get small. All right. But what we're saying now is pretty close to the same thing, except for we're not going to be approaching a value from a single direction or even two directions. What we need to do is approach a point in our domain, this x sub 0, y sub 0, from all directions, from a delta neighborhood around a particular point. So let's say we were trying to approach this point in our domain, okay? We have to approach that point from a delta neighborhood around it. So from this direction, from this direction, from this direction, okay? And as we do that, as this delta neighborhood shrinks down and we get closer and closer and closer to this point, the corresponding y values, the f of xy, which these are our z's, remember, have to get closer and closer to L such that the difference between them gets very small, is less than epsilon. So then this distance here of all these corresponding z values are getting closer and closer and closer to this particular z value here. And again, this picture kind of defines that. So here we have an open disk around this point AB, kind of project that up onto the surface. You get all these z values here, and these z values have to be shrinking in closer and closer to this particular z value for that z value or that limiting value L to be the answer for the limit. Now, the problem here is you have to approach this from all directions. It's not from the left and from the right. It's from the left, it's from the right, it's from this direction, it's from this direction, from this direction. It's this disk all the way around. So 360 degrees all the way around a point. Every single one of those has to continually approach the same z value. So this is pretty hard here to sort of see whether or not this limit's going to exist or not, unless you're kind of looking graphically at it. But that's what this is saying. When this distance is smaller, when this distance is smaller, which this ring around some point gets smaller, then the distance between the z values and the limiting value also gets smaller, which is your basic definition of limits that you learned back in Calc 1. You did it just in terms of delta and epsilon as these two linear distances. Now we're doing it as delta and epsilon essentially are these circular, almost radial distances. So basically what this is telling us is it implies that for every point x, y that's not equal to x sub 0, y sub 0 in the disk that has some radius delta, so it's in that delta neighborhood, the value of f of x has to lie within that distance. So L plus epsilon, L minus epsilon. So the limiting value has to be within a certain distance here. It has to get smaller. So, we would approach x equals c from the left and from the right, but now we have to approach from infinitely many different directions around the point, from this ring around the point. What you're going to see that it's actually easier to show that a limit doesn't exist than to find that a limit does exist. Because to show that a limit doesn't exist, you just have to show two paths to get to this point where you don't get the same z value. Whereas to show that it does exist, you basically have to show that infinitely many ways to approach this particular point yield the same function value, the same z value. And that's going to be very difficult to do. But we'll have some quick, easy examples of how to get this done. So here's one where I'm going to ask you to show that the limit doesn't exist. And like I said, oftentimes this could be easier than showing the limit does exist. Because what I need to do is show two paths that get me to 0, 0, where I don't get the same function value, the same z value. So I'm approaching 0, 0. So if I think about my domain as a set of points in the xy plane, here's 0, 0. That's the point I'm trying to approach. And I have to approach that point from infinitely many different directions. So from this ring around this point, and make this ring shrink down further and further and further till I get to that point. So I would have to approach it from every one of these directions. And every time I approach it from one of these directions, the corresponding function value is the same every time. So in order to show that it doesn't exist, I just have to find two ways to get to 0, 0 where the function values are not equal. Okay? So something like what we would have said in Calc 1, where the limit from the left and the limit from the right don't equal each other. Okay, that was your basic idea, right? You had a limit, so you had a function that looked like this, and you had a function like this, right? And I was approaching 0, there's one value 0. As I approach 0 from the left, I get this y value. As I approach 0 from the right, I get this y value. So the limit from the left and the limit from the right were not the same, therefore the full limit didn't exist. Kind of the same thing, but I got to show it. Any two random ways to get to 0, 0 are going to give me two function values that are not the same. So that's what I'm doing here. Also notice that 0, 0 is a discontinuity for this function in that it makes the denominator equal 0. So the function itself doesn't exist at 0, 0. Okay, that 0, 0 point is not in the domain of the function, but that's okay. Remember, a function doesn't need to exist at a location for the limit to exist as we approach that location. That was a big idea you learned about limits, is that limits aren't about what happens at a value. Limits are about what happens as you get close to a value. So 0, 0, just note, is not in the domain of this function, which is what makes this a little bit more difficult, and therefore part of the reason why the limit's not going to exist. Anyway. Not complete reason, because a function could not exist and a limit could exist. So anyway, let's see this. So let's look at a couple of ways to get to 0, 0. The easiest ways to get to 0, 0 to kind of work with at first would be along the axes. So let's approach 0, 0 along the positive x-axis. Okay? So all these points here are getting me closer and closer to 0, 0. One thing all those points have in common is that they have some positive x value that's getting closer to 0, but the y value for every one of those points is 0. Okay? That's something that you should note. So the idea here is that we are doing the limit as we approach 0, 0, but the points are points x, 0 are approaching 0, 0. In that the y value is staying 0 the whole time, the x values are now really what's approaching 0 for this function 3xy over x squared plus y squared. So if the y values are 0 all the time, y isn't approaching 0, the y values are 0. Every one of these points has a y value 0 the whole time. I could fill 0 in for y and write this as the limit as x, 0 approaches 0, 0 of 3x times 0 over x squared plus 0 squared, which would ultimately give me the limit as x comma 0 approaches 0, 0 of this whole thing would just be 0 over x squared, which 0 over x squared would be 0, so I have the limit as x comma 0 approaches 0, 0 of 0, and therefore I really am just taking the limit of a constant, and the limit of that constant would be 0. Okay? Remember, basic rules of limits. Limit of a constant is that constant. So what I found is that as I approach 0, 0 along the positive x-axis, the limit value is getting closer and closer to 0. That's what the z values are doing. Okay. Now let me look at it from a different direction. Well, another easy way to get to 0, 0 is along, say, the positive y-axis. And if I look at all these points getting closer and closer to 0, 0, what happens? Well, they all have something in common as well. The x value for all those points is 0, and then I have some random y, but that y is getting closer and closer to 0. So this point would be a point, say, 0, 2, and then 0, 1, and then 0, 1/2, right? These points are getting closer and closer to 0, 0. The x's are staying the same the whole time, but the y's are what is shrinking down to 0. So if I do that, that's basically saying I'm doing the limit as 0 comma y is approaching 0, 0 of this function 3xy over x squared plus y squared. And as I do this limit, if I get something other than 0, that's showing me that as I approach 0, 0 from two directions, I get two different things, and therefore the limit will not exist, because I have to keep getting the same function value no matter which way I get to 0, 0. Well, the problem here is I actually don't get something different. If I do this one, I'm going to let x be 0, so I have the limit as 0 comma y approaches 0, 0 of 3 times 0 times y over 0 squared plus y squared. What you end up getting here is the limit, it's right over here, the limit as 0 comma y approaches 0, 0 of 0 over y squared. All right, this is 0, this will just give me y squared, which is really just going to be 0 over y squared is going to be 0, so the limit of 0y approaches 0, 0 of 0, limit of a constant is still just that constant. I end up getting the same thing. Now what does that tell me? Well, actually it doesn't tell me anything. It just tells me that as I approach from these two directions, I get the same z. That doesn't mean the limit exists, because there's a lot of other ways to get to 0, 0, right? I can get to 0, 0 here, here, I can get there on an angle, I can come swooping in on some random function and then get to 0, 0. I mean, there's a lot of ways to get to 0, 0. So let's try and find another one. And hopefully we get a different z value out of this, and that'll show that the limit doesn't exist. Well, here's one more that we're going to look at. Let's look at this line right here that goes through 0, 0. And that line is a 45-degree line, and the line is y equals x. Okay? So the y equals x line. So here are the points that are on the y equals x line. They're getting closer and closer to 0, 0. They'd be points like 3, 3, 2, 2, 1, 1, etc. Right? They're getting closer and closer to 0, 0. So what do all these points have in common? Well, the things that they have in common is that the x and the y are the same. So I could write this as the limit as x comma x gets closer and closer to 0, 0. Right? The x and the y are the same. So rather than call them x and y, I just call it x and x, because they're the same value in both registers, the first and the second. So if I do that for 3xy over x squared plus y squared, well, rather than have x's and y's, I could have all x's here, and I can say, well, it's the limit as x approaches 0, 0 of 3x times x over x squared plus x squared, which would give me the limit as x approaches 0, 0 of 3x squared over 2x squared. Well, notice these x squareds can cancel, so I have the limit as x approaches 0, 0 of 3 over 2. Still just a constant, and the limit of a constant is that constant, which in this case is now 3/2. Well, guess what? We just got a different value that the function's approaching on that path than these other two paths. So the limit from the x-axis, the limit from the y-axis may equal each other, but the limit as we approach along the y equals x line is not the same. And therefore, since these two directions, either this one and this one or this one and this one, are not the same, therefore the limit doesn't exist. So you would write a little something like, let's clear some of this out. So since the limit along the positive x-axis does not equal the limit along the y equals x line, the limit does not exist. Okay, something like that. And the idea is you can show this as long as that happens. Now, let's say that this also gave us zeros for the answer. Does that mean the limit exists? No. You have to continually get to 0, 0 from all these different directions and keep getting the same function value, which is impossible to necessarily show because there's infinitely many ways to get to 0, 0. It's this ring around 0, 0 that's going to keep shrinking down and get there. So it's very hard to show that a limit exists, formally in sort of this regard, but it's very easy to show a limit does not exist. Well, I shouldn't say very easy. It's easier to show a limit doesn't exist because you can do it through a series of trial and error. Now that's not to say that we can't evaluate a limit and get a value for it that show that a limit does exist and what the answer is. There are some very easy ways to do that. Think about it when it comes to a function that is continuous. If a function is continuous everywhere around a particular point, then the function value and the limiting value were the same in Calc 1. Well, it's the same thing here. If I'm trying to approach this point 2, 3, so 2, 3 is in the domain of this function. Why? Because it does not make the denominator 0, so the function is continuous at 2, 3. Okay? Well, it exists, I should say, at 2, 3. And this function is continuous everywhere around 2, 3, then I should be able to just plug 2, 3 into the function, and the function value should be the same as the limiting value. So if I wanted to evaluate this limit, it's as simple as saying, okay, I have this function fxy, which equals x squared y minus 2y over 7x minus 5xy. If I was just evaluating f of 2, 3, if I just plug 2, 3 right in because I can, then guess what? I would get 4 times 3 minus 2 times 3 over 7 times 2 minus 5 times 2 times 3. And whatever I get out of that, which would be 12 minus 6 is 6, over 14 minus, 30, so that's negative 16. Simplify, you're going to get negative, 3/8. So the limit as xy approaches 2, 3 for this function x squared y minus 2y over 7x minus 5xy is just negative 3/8. It's as simple as plugging in. Sometimes you saw limits were as simple as just plug the point into the function, and there's your answer. Now, you didn't get lucky enough to have a lot of these examples back in Calc 1, and you won't be lucky enough to have a lot of them now. But because the function is continuous at and around 2, 3, you can simply just plug 2, 3 into the function, and that would be the limiting value. Now, as you know, that didn't always happen. Sometimes you couldn't just plug the value right in, and most times you couldn't. So here's an example of that. If I were to plug 1, 1 into this function, what would happen? I would get 0 in the denominator. I would also get 0 in the numerator, so this thing would be getting closer and closer to 0 over 0, which we know is an indeterminate value. That doesn't mean the limit exists or doesn't exist. It just means it's indeterminate, and I can't plug 1, 1 in. So what am I going to do? Well, think about some of the tricks you learned along the way in Calc 1. One thing you did lots of times in Calc 1 is you took a function, you used factoring to help rewrite the function as another function that would then help you evaluate the limit. And we're going to do the same thing here. So if I have the limit as xy approaches 1, 1, I'm not going to try and prove that this limit doesn't exist. I'm just going to go ahead and evaluate the limit. But the way I'm going to do it is not by plugging 1, 1 in right now. What I'm going to do is I'm going to first factor that denominator, which is a difference of squares. I'm then going to cancel these common factors and rewrite this function as the limit as xy approaches 1, 1 of now 1 over x plus y. Now I have this new function, which is, related to the original, but not the same. Related to the original in that this function and this function equal each other everywhere around 1, 1, except for at 1, 1. At 1, 1, this function doesn't exist. However, at 1, 1, this function does exist. So since they're equal to each other everywhere around 1, 1, then the idea is that the limits should be equal. So now I can plug 1, 1 into this function, no problem. So I have the limit as xy approaches 1, 1 of 1 over x plus y, and that should give me 1 over 2. Why? Because I plug 1 in for x, 1 in for y, that would give me 2. So the limit is actually equal to a half. And this is a very common trick you did in Calc 1. I mean, think about it. If I said, let's do the limit as x approaches 2 of x minus 2 over x squared minus 4. Okay? In this case, you couldn't plug 2 right in. What would you do? You'd factor this denominator as x minus 2, x plus 2. You'd cancel the x minus 2's. You would have the limit as x approaches 2 of 1 over x plus 2. Now you got to the point where you plug 2 in. What do you get? You get 1/4, and you get your answer. Well, that is really not much different than what we just did. And sometimes you can use some of those tools from Calc 1. Overall, the idea really is just understanding how these limits in multivariable functions work, about this open disk collapsing down on a particular point you're trying to approach, and all the z values approaching that exact same z value. We really just need this so that we can get into the definition of derivatives. So we're not going to spend much more time talking about limits other than that. One thing I want to do real quick, though, is talk about continuity, because continuity and limits really go hand in hand. Remember in Calc 1, in order for a function to be continuous at a particular point, okay, at some point x equals c, 3 things had to be satisfied, and all 3 things had to be satisfied for you to be continuous at a point. 1, the function had to be defined at that particular location. F of c had to exist. 2, the limit had to exist as you approached c. So as you approach c, the limit exists, okay? And then the third thing is that the first and the second had to equal each other. The function value and the limiting value had to be exactly the same. And so you had a couple of scenarios here, like here's one where you have a function like this. There's an open circle, and then here's a closed circle right above it. The function at, say here's c, the function at c exists, and it's whatever this y value is. The limit as I approach c from the left and right also exists because it's whatever this y value is, but the problem is they're not the same. Therefore, I have this hole in the graph and I have a discontinuity. As opposed to if my graph looks like this and it's solid all the way through, then this is continuous. Why? Because the function value exists. It's right here, whatever that y value is. Say this is c. The limit as I approach c exists, and it's that same y value, and they're equal to each other. Therefore, all 3 things happen, and I got a continuous function. So that's something to remember from Calc 1, because then we're going to use that exact same thing to define continuity in the multivariable situation. So in looking for continuity of a multivariable function at a particular point, we basically do the same thing. So 3 things need to happen. 1, the function has to exist at a given value. So you have to be able to find f of x sub 0, y sub 0. 2, the limit as you approach that point has to exist. Okay? And this, let's fix this. This here should be x sub 0, y sub 0. That's what you're approaching. You're not approaching 0, 0 necessarily. You're approaching x sub 0, y sub 0. Well, anyway, the limit has to exist. And thirdly, those 2 things have to equal each other. Okay? And so that'll show you that, essentially you have continuity at a particular point, x sub 0, y sub 0, for a given function. So all three things have to happen. Now, largely we don't go through this test for every point on a function. We don't make sure that the function exists, that the limit exists, and that they're equal to each other. What we've done is use what we know about functions, and we should be able to look at certain functions that are very common and know that these three things are going to happen, or maybe one of these things isn't going to happen, and therefore we could find a discontinuity. And so if I gave you a couple of examples like, say, these are very, very common examples. We have a polynomial example. We have two rational examples. We should be able to look at these and know whether or not these functions are going to be continuous or not at given values, or where they might be discontinuous. So for the first one, we got to find all the points x and y such that this function exists, the limit as I approach all those x and y's exists, and they're equal to each other. Well, since it's a polynomial, we know that's going to happen for every point. So where is this function continuous? Everywhere. It's continuous for all x's and y's in the domain. And the domain consists of all x's and y's, where x can be anything and y can be anything. Why? Because it's a polynomial. That's not the case for our rationals. Our rationals, what do we know? We know the denominator can't equal 0. So all the x's and y's that make this denominator 0 essentially will make the function not exist and therefore discontinuous. So which x's and y's will that happen? Well, those x's and y's that'll make that happen will be all the x's and y's such that x equals the absolute value of y. Those would be all the points. So points like, 1, 1. If I put 1, 1 in here for x and y, that would make the denominator 0. But also 1, negative 1. Or even negative 1, 1. So all the points where the absolute value of x equals the absolute value of y, maybe I should say it that way, might be even a little bit better. Those are all the places where it's going to be discontinuous. And so you should just be able to look at this function and know what points you can and cannot plug in, and what points will make this thing continuous and which ones will make it discontinuous. Just because you know basically what happens with rational functions generally, and when they're continuous and when they're discontinuous. Same issue here. The problem here, though, is we get a plus here. So there's only actually one point that is going to make that denominator 0, and that would be the point 0, 0. So we could say that that function is continuous everywhere but 0, 0. And so if you were to look at this and say, like, the xy plane, so here, let's erase this. And let's look at the domain for each one, and I'll look at it in a graphical standpoint. So for A, the xy plane is where the domain should reside, all the x's and y's. And essentially, the entire plane is your domain. Okay, so all x's and y's, the domain is the set of all x's and y's such that x is between negative infinity and positive infinity, and y is between negative infinity and positive infinity, right? So that would be that one. For B, what do we say? We said that really, if we think about it, the points that we don't want are where the x's and y's are on the absolute value. So essentially, these points and these points would be the points that are not in my domain. So my domain would basically consist of everything in this triangle, this one. They're not really triangles, but in this space, and this space. Anything that sits on these lines, this line would be y equals x, and this one would be y equals negative x, okay? Anything that sits on those lines is not in my domain, so my domain would consist of, everything in that purple space. And the last one, C, if I look at it as a set of points, then this point right here, 0, 0, is the only point that's not in my domain, so my domain would basically be every other point in the xy plane except for that point right there. And so we look at domain that way. And then we talk about continuity. So the function would be continuous everywhere because of its domain. Here the function would be continuous everywhere except for any points that are on these two lines. And here the third function would be continuous everywhere except for this 1.00. So largely that's how we think about continuity when it comes to functions. You just look at the function and you know, okay, these are the places where it's continuous and this is where it's discontinuous. But ultimately what you really should do is you should prove the three things is, does the function exist? Does the limit exist as we approach that value? And are they equal to each other?